Hello and welcome to all the viewers. In this video, we will going to discuss about transient structural analysis of engine assembly using ANSYS Workbench. So basically, we will going to perform first rigid body dynamic analysis for this respective engine assembly, and then we will going to copy the same deck and we will perform the transient structural analysis. So this slide represents the learning in this video. Very first we will discuss about the problem statement. Then we will move towards our analysis part. In the first part we will going to cover about how to perform rigid body dynamic analysis in ANSYS Workbench. So there we will going to discuss like how to define different joint definitions, then how to apply a joint load, and at the last we will discuss about the results like the joint probe for the applied joint load. Then we'll discuss about the how to see the deformation for the applied joint load, and then in next we will perform the transient structural analysis where we will make any one component a flexible one, and there on that respective component we will apply a joint load in the form of gas load, and then we will see the respective result like same joint probe, deformation, the energy summary. So this slide represents our actual problem statement of our present video. Here it says to perform a rigid body dynamic as well as transient structural analysis of engine assembly using ANSYS. So as we know that engine may consist of like your casing, outer casing, your crankshaft, your connecting rod, then your pin which connects the connecting rod, and piston. You will find our piston. Okay, so these are the major components of any engine assembly. For present analysis we are considering simplified single cylinder engine. Now here the first statement is like we need to perform rigid body dynamic analysis. So as name suggests, when we consider rigid body dynamic analysis, in that case all parts should be rigid one. So here we need to apply a 75 Newton downward force on the piston. So basically, so this force drives the piston movements, up and down movement. So we will going to apply a joint force of 75 Newton for a joint between cylinder as well as this casing. And the next part we need to perform the transient structural analysis, that is rigid as well as some flexible parts. So assume connecting rod as a flexible part and find out the stresses on for the respective joint force load. So when we replicate this rigid body to transient structural, there we need to make few of the parts flexible for which we are performing the simulation, or which is the scope of the simulation. So that part should be flexible one. Okay, now what we'll do, we will go to ANSYS and there we'll discuss the present simulation. So now we are in our ANSYS mechanical workbench window. So here I already performed that simulation, so I will further redo the simulation in front of you so that you will get the complete insight of how to perform rigid dynamic as well as transient simulation. The very first step that you just need to drag and drop your analysis system from here. Just simply double click over here, and once your rigid dynamic analysis deck you will find on this design window, you just right click here and you can import your geometry either in Spaceclaim or design modeler. Once your geometry is imported and if you found that there is no issue, then simply go to the mechanical. So now you can see that our geometry is open in mechanical. Let's display all the parts. Okay, so the very first part to check whether it is all parts are rigid or not. So by default it should came as a rigid. You can see all the components are rigid one. Okay, now the material, let's take by default that is the structural steel, and now there is no significance of that anyhow. Now the next step is to define the joint. You will find automatic created a contacts over here, but here we will going to define the joint instead of the contacts. So let's create the various contacts. Okay, in order to create the contact, you just need to go to connection, right click, insert, and then create a joint. Let's start the very first joint. So here let make it more, and let's make the body to ground and select this component, apply. Either you can select the some part of this face, or you can even select the whole outer faces of the this respective top casing. Okay, and here as we know that we are going to consider this as a fix, because somehow this will going to connect it with the another assembly of the engine. That's why we are just making it as a fixed ground. Either you can make this or you can make this, both way you can do the fixed contacts. Now let's hide this and let's define the another contact, that is cylindrical one between. So here you just go and select the cylindrical contact, select the face, apply, right click, show all bodies, hide all other body, and here you can define the contact between cylinder outer surface, inner surface, and piston outer surface. So we are defining here as a cylindrical contact. So what do you mean by cylindrical contact? So you can see over here definitions, like it says that your z axis as well as rotation about z axis is free. Okay, now we want the same, like due to the respect to gas force, this piston should move up and down so that it can operate the crankshaft and then engine. Okay, now let's define the another contacts. So for that, let's go with this, hide all other body, and right click, insert, and join. So what do you think that what will be the contact between this and this connecting pin? So if you go here, the type, you will find there are different number of contacts are there. So these contacts are based on the relative motion between the components and between the body. So for present, between the connecting pin and this piston, as we know that there is a revolute movement, so that's why we need to consider the revolute joint between these two faces. Okay, these are the two faces, and here you should consider show all body, hide all other body. So here instead of that face, just select this face. Okay, now if you want to check whether you define properly or not, just right click, hide all other body. So likewise you can see whether you define or not correctly. Now let's define the another furthermore similar revolute joint between this and between the connecting rod, hide body and hide body. Let's define this face. Okay, so likewise you need to define the respective revolute joint between the connecting rod pin, and then piston. Now in similar fashion, let's define the joint at the bottom face, insert, join. Let's select this face, hide all other bodies, select this face. Okay, now this should also be the revolute joint. Now the next joint should come between this and this. So there are two ways. The first way is like you can simply define joint between this face, make it revolute, and either you can define between this body or else you can define between body to ground. Let's make it revolute so that it can move with respect to the ground stiffness. Okay, this is the first way. The another way is like make it suppress, hide all other body, create a joint, show all bodies, hide all other body. Here the between bearing we are defining, bearing we have not model. So likewise you can even define with this revolute. Okay, this is the another way. Or now let's check. Now you have defined the contacts, joints. Then the question will come into your mind, like how to check whether joints are defined properly or not. What are my degrees of freedom? So for that, you just need to go to the connection, go to the worksheet, and here you just need to generate. So here it will show the all the contact, all the joint definitions along with the scope and references, along with the status, and here it will define the all the respective degrees of freedom for the respective joint. So here at present it is showing that there are 6 degrees of freedom are free. So always keep in mind it should be 0 or more than 0 just to work the mechanism. Okay, so always need to check whether these are over constraint or not. So right now it is free. So why it is free? Because if you remember, we defined this revolute joint, but there is no fixed joint between these two bodies or between this or body ground. So that's why it is showing that fixed joint, 6 degrees of freedom. Now let's define insert joint, show all bodies, hide all other body. There is no significance actually for present simulation of this respective body, but just for the sake of analysis I consider the whole. Now let's check, go to connection further and then click on the worksheet and generate. Now you can see that are constrained, that respective body is constrained now. Okay, that's why it is showing 0 -4. Okay, now either you can keep this between this face and this face, or else you can define between this body to ground. Both way you can define the respective joint. Okay, so this is what the very important term when you talk about rigid body dynamics. You should know how to define the joint. You should know the different joint aspects like cylindrical, revolute, what is fixed joint. You can refer our blog post, that www.graphengineering.com. There we define what are the different kinds of joint, and we started writing the blogs on respective joint also. Now the next part is to define the analysis setting. So here we are making the simulation in 2 steps. Okay, the first step which says that it should end at a 0.1 second, and here you can define this time step, like whatever the time step, you can either define the time step or you can make it off, but it is better to go with some finer time step. So I will explain this in more in a transient structural simulation. Okay, now let's define the second load step should end at a 0.2 second. Okay, now here the same like initial time step, like it should start from 0.1, then the minimum it should go up to 1 e raised to -3, and the maximum it should go up to 0.05. Okay, likewise we define the respective time step. Now let's define the joint load. So what we can do, we can simply go to this joint and just drag over here on this respective joint. Let's define the Z displacement, let's define the force, and let's define the magnitude. So as we know that our magnitude should be on the piston, so let's make it -75. Okay. Now you can see this axis, and for this respective joint, let's extract the total deformation. Let's extract the joint probe for a joint for cylindrical. Okay, you can check the total force, or you can check the total force in a z-axis. Right click, insert probe. Let's check further a joint probe and check for this respective joint the relative rotation z-axis. Okay, now right click, solve the simulation. So this simulation will not take a longer time because it's rigid. It does not perform any mesh. Now we can see that our simulation is performed. Let's check the deformation. So for that, let's make it hide the body. Let's check deformation and let's rotate. Now we can see that it is showing it's going for the 25 downward, and then further it is to and fro motion. This is because the applied force, we kept it minus 75 and then further we kept it minus 75. So what we can do now, let's deactivate this and let's run further. So now we will get the smooth movement. So after first step we are saying that minus 75 is the load and it should carry next onwards, or it should be the mitigate. Now let's check the deformation and let's animate the result. So now we can see that okay, we are seeing the same load carrying in the second stroke. Okay, likewise it is going. Now let's check the joint probe. Now you can see that for the respective joint probe in z-axis how it is applying with respect to the time step. Now you can see that the respective joint force. Now let's this next step, that is relative rotation z-axis. So like this you need to perform your rigid body dynamics simulation. The very important term is that here you should know the joint definition. Here you can define the various joint loads, as well as you can define acceleration, standard earth gravity, remote forces, joint loads, remote displacement, and even you can define the constraint equations. And for the same you can even check the what is the deformation velocities as well as acceleration as a output. So the main importance of this simulation is that you can extract the various joint loads for the applied joint forces. So these simulations are useful for for example earth moving equipment, excavators, which are subjected to the various joint loads. So we can study with the help of multi-body dynamics the various joint forces, and accordingly we can design the respective joint. Okay, now this is all about our rigid body simulation. Now the next step is we need to perform the transient structural simulation. So now for this second deck you just need to duplicate this. Okay, you just need to duplicate. Once it will duplicate, then the next step is you just need to replace this with a transient structural. Okay, so likewise you need to duplicate and then replace with the transient structural. What it means that we are using the same deck and we are just making it as a transient structural. So when it is done, then double click over here and then you will find that the same deck is carried in a transient structural simulation. But here, as we know that we need to make a few parts as a flexible one, and at present we are studying connecting rod, so that's why let's make connecting rod as a flexible one over here. Okay, now once you will make flexible, it will show that the cross green mark is removed. So basically this internal coordinate will not present for that. Now make it the same material. Then regarding connections, we will going to use the same connections. Now mesh, it will auto generate the mesh for the flexible component. Okay, now make sure there is one more thing, like in analysis setting you will find that this is disturbed though we copied the same deck. It is because the analysis setting in rigid body dynamics as well as in transient structural is different one. Okay, so let's make it I will say that initial time step should be 1 e raised to minus 2. Okay, and it should go minimum up to 1 e raised to minus 3 and maximum it should go up to 0.1. So what does it mean? That as we know that it will go under the convergence issue, so that's why it is better to start the initial type step 10 times your time second. Okay, that is the initial time step. And suppose though it is started at this, it will not converge, then you can say to the software that it will further divide by the 10. So basically 100 times you can divide the sub step and it will apply a minute number of joint force. Okay, so that is the significance of this minimum as well as initial time step. So let's repeat the same in the second load step. So let's define this as a 0.01. This is the 0.01. This is the initial time step, and then it should go up to the 0.001, and maximum it should go up to this. So basically it will start at the initial this, and between this to this it will going to range as per the force applied. Okay, now the next step is insert deformation. You can see the total deformation, you can see the stresses on the respective member. So basically it will show the stress on a flexible body, and let's check the proof for the energy one, and let's solve the simulation. So we will keep the same by default mesh size. It will take some time because it is not the rigid dynamic simulation, it is this transient structural simulation. Now if you see that our simulation is performed for the applied joint load. So joint force is basically the output of, as we know that it is varies in terms of your respective time as it is transient load, and for that you will find the deformation is, let's hide this component, let's check the deformation. You can see like deformation, I will uncheck the mesh. So even you can insert deformation for that respective body also, you can check the deformation. Okay, and make it all bodies. Now check how it is deforming. Okay, you will have the similar kind of deformation what we studied in case of rigid body dynamics. So the maximum it's deforming up to 61 mm when we make it flexible. Now let's check the joint probes. Okay, this is the joint probe. Similarly over here joint probe is similar fashion. Now here the energy probe is important one. So here as we know that the only energy which is driving is the kinetic energy because there is no restriction. So now we can see that due to this there is only the kinetic energy is present, as so you can see kinetic only, the strain energy is constant one. Okay, because there is no restriction for the respective applied load. So that's why even you can see the stress values is also the minimum one, or there is no stress because it is allowed to move up and down. There is no restriction. Suppose if you make it instead of revolute, if you make it fixed one, then in that case you will find the high stress value. So likewise you can check the respective stress as well as deformation for the transient structural simulation of the engine assembly. So here also you will have, there are various loads are there. Dynamic simulation you will find that pressure forces, remote forces, these loads as similar to our regular FEA simulation, and here you can extract the various loads. Okay, in terms of your deformation strains also you can see stress energies. So that's it guys, that is the conclusion of our present video. Let me know your comments. The purpose of this simulation, you should know how to perform rigid dynamic as well as you should know how to perform the transient structural simulation. So thank you guys, let me know your comments, I'll be there to help you. Bye bye, take care.